this class. Perfect. Okay. So again, we're doing 11-1, but before we do that, we're going to practice a few things from the end of circles that again was not on your test, but like will be on the next assessment that you do. So I'm going to draw a circle. I'm going to draw a circle. And then I want to draw some kind of quadrilateral on the inside. So something with 4 sides. Okay, of course I did that very, very close. I tried my best not to make it look like a square or rectangle so that you didn't think that certain things were congruent or not. So I've got these this quadrilateral that's inscribed in a circle. So we call this part inscribed quads. So they're quadrilaterals inscribed in a circle. And so I'm going to label these little angles as such. I'm going to call this one 25y plus 4. I'm going to call this one 21y plus 3. I'm going to call this one 9x minus 5. And I'm going to call this one 9x plus 12. Okay, so what I've got going on here is I've got this quadrilateral. And I know a couple things about this. I know that my opposite angles are supplementary. And I know that they don't have the same variable. So we're going to have to set up a systems of equations. So we're going to set them equal to 180. So we've got two things. We're going to set them equal to 180. What I am going to do is once I do that, I need to make sure to combine all my like terms and just get x plus y equals all my other numbers on the other side. So I'm going to write that. Over here. I'm going to write that over here. And I'm going to use a different color for each one. So I've got this yellow one. I'm just going to write it in purple because we can't see yellow. And so I've got 9x minus 5 plus 25y minus 4 equals 180. Oop. It's plus 4, excuse me, plus 4. So I've got plus 4. Before I write the other one, I'm going to combine my like actual constants and then move them to the other side. So I've got 9x plus 25y equals negative 5 plus 4 is negative 1. And so then I have to add it to the other side. So I get 181. So that's one of my equations. Now I have to do my other equation. My other equation is this like orange one. So I've got 9x plus 12 plus 21y plus 13. 9x plus 12 plus 21y plus 3. And this still equals 180. So remember, opposite angles are sup. So that's why we add them up, set them equal to 180. 12 and 13 is 15. So 9x plus 21y equals, I have to minus 15 from both sides. 180 minus 15 is 165. Okay. This is actually best case scenario because my two equations, I've got 9x blah, 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 and I've got 9x blah, 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 blah. I already have two terms that are the exact same. I just need one of them to be minus. So I'm going to make the second one all minuses, and I'm going to rewrite them together and eliminate using those two equations. So my first one is, I didn't change, 9x plus 25y equals 181. My other one is going to be, again, everything becomes minus, 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 minus. There's only 3 minuses. I got a little carried away. And now I get to cross out my x's and I get to combine to find my y. So 25 minus 21 is 4y. 181 minus 165 is going to be 16. And then divide by 4, y equals 4. I'm going to use that to find my other one. I'm going to use that to find my x. So I'm going to take any equation that I've already done. I'm probably going to take the one that I have highlighted in yellow and make that be the equation I use to find my x. So I'm going to do 9x plus 25 times y, which in this case is now 4, equals 181. You can plug it into this one or the orange one instead. It really doesn't matter. Just be consistent and plug it into one of them and solve for x. So once I do that, I get 9x plus 100 equals 181. You minus 100 from both sides, so I get 9x equals 81, and I divide by 9 and I get x equals 9. Once I find those, I can plug those into my equations and find out what my actual angles are. So again, I'm walking all the way through this because I'm going to ask you to do one by yourself in a second. So 9 is x, y is 4. So I've got 25 times 4 plus 4 is going to be 104. Now I've got 21y plus 3. 21 times 4 is going to be 84. Plus 3 is going to be 87. Okay. 9x minus 5 is going to be 81 minus 5, which is 76. And then 9 times 9 plus 12 is going to be 93. Okay. Anybody have any questions on the math of this so far? Because I'm going to give you another one to solve. Okay. What I'm going to do then is I'm going to just draw it in the same shape. I'm just going to erase this all. Anybody have any questions or thoughts before I erase it? Okay. Let's make it this. So now these are my new sides, or my new angles, excuse me. I've got 45y. I've got 1 plus 44y. I've got 31x minus 3, and I've got 31x minus 2. So I want you to take a minute and I want you to try and solve this. I'll erase the rest of my work over here. So I'm going to be quiet. You try to solve this for a second. Okay, if you didn't know where to start, I'm going to write my equations now. Again, you can't just write your x's and y's together because you want to. We have to write what actually goes together. So I've got 31x minus 3 plus 45y equals 180 let's move the 3 over. I got 31x plus 45y equals 183. And then I got the other one, which is going to be 31x minus 2 plus 1 plus 44y equals 180. So that's 31x plus 44y, and that becomes -1, so it becomes 181. Looks like I gave you a couple easy ones. That's my bad. I should have made it a little bit harder. What I need to do now is to make one of these minus all the way across so that I can cancel it out with my elimination. So I'm going to make all of these minus. So when I rewrite it, I get 31x plus 45y equals 183. Again, I'm just copying this down. I'm going to take the blue equation and copy it down. So minus 31x minus 44y equals negative 181. And I get to combine. So it gets me y equals 2. Oh, that was easy. And then now I can plug it in anywhere. I can plug it in. I'm going to plug it back into this one up here. So I've got 31x plus 45 times 2 equals 183. 31x plus 90 equals 183. When you minus 90 from both sides, we're going to get 93 left. And then 93 divided by 31 is 3. That worked out very nicely. So now you got to plug 2 in for all your y's. You got to plug 3 in for all your x's. And I got to go on with that. So 45 times y is 90. 44 times 44 times 2 plus 1 is going to be 89. 31 times 3 minus 1 is going to, or minus 3, excuse me, is going to be 90 as well. And then 31 times 3 minus 2 is 91. So all of these were super close together, but you can see that 91 and 89 are supplementary, and 90 and 90 are both supplementary. So again, we did 2 extra bonus problems of that just because I wanted to remind you that this is fair game for the next assessment. Again, I haven't committed to giving a quiz or a test or a quest. It's just going to be something over the next 3 days of lessons. So just be prepared to get an assessment over any of that. Anybody have any questions yet? Okay, again, I just made those up and I'd be happy to do more of these problems if you were having a hard time with them. What we're going to move into now is like actually today's lesson 11.1. It's about 3D figures and areas of regular polygons. So what we're doing today is just basic. We're starting our 3D shape journey, but we're really focusing on how to find the area of shapes that aren't like parallelograms or triangles or trapezoids or anything. So just a regular polygon. In the next 2 days, we're doing surface area and we're doing volumes of different shapes. So we just got to be ready. There's a lot of formulas kind of coming our way. So we're just going to deal with those one at a time. Before we get started, though, we have to do a couple vocab things. So again, we're starting our world of 3D shapes. So this new shape that we're going to talk about is something called a polyhedron. A polyhedron is a 3-dimensional shape whose all of its surfaces are polygons. Remember, a polygon is a shape with like straight edges. There's nothing curved. There's nothing crazy. It's just like straight edge 3D shape. The word polyhedron comes from the Greek word meaning poly, which we know means many, and then hedron meaning base. So essentially there's a bunch of different bases of my shape. We don't call the surfaces bases. Instead, we call them faces. Like a little smiley face. You know, that guy looks a little crazy, but like a little smiley face. They're all faces of the shape. Top face, bottom face, front face, back face, whatever you want to call it. There's 2 other things that we need to think about when we're looking at a 3D shape. Faces, which I want you to think about, faces are planes. So that's like, remember we learned points, lines, planes at the very beginning? Faces are like the planes. It's like a piece of paper, it goes straight and it goes forever and forever. And in this case, until like we tell it's going to stop, because like the cube ends or the cylinder ends or whatever the prism ends. And the faces, the planes, intersect at what we call edges. It's like a tissue box. It connects at the edge of the tissue box. I don't own any tissue boxes in my house, so this is kind of awkward. And you can think of edges as like segments. We don't call them lines because they end. Like the tissue box ends. It doesn't like go on and on forever. That would not really work. Can't really take the tissue box anywhere. And then edges meet at what we call vertices. And another thing to think about for vertices, those are like points. So again, we're talking about these 3D polygons, which we call polyhedron. That's a fancy name for a 3D shape. Their surfaces are called faces. The points where the faces intersect is called the edge, and then the edges meet at points called vertices. So we're gonna do some identifying that in a second. All right, first example, it says cross out the figure below that is not a polyhedron. Something that's not a polyhedron means that you can't have a polygon as its side. So the first couple, those both have polygons as sides. There's triangles, there's rectangles, there's squares, all that fun stuff. Same thing with the last one, it's squares and rectangles. The third one, that's the one that does not work because I have a circle as one of my bases. A circle is not a polygon, it's a circle. That's its specific shape. So polygons have like edges and straight lines. They don't have any curved lines, they're straight. So this cylinder looking item is not a polyhedron. All right, the next thing I'm going to do is I'm looking at this shape. I think we call it a prism most exactly, but it kind of looks like a piece of cheese or like a door stop that you like shove into the door so that it doesn't swing back closed. And so we're going to think about faces, vertices, and edges here. So I think faces is the easiest thing to start with. So we're thinking about like, where are like the planes? Where are the sides of this shape? The easiest ones I think of are the triangle ones, the like front one and the back triangle one. Those are faces. Remember, it's been a while since we've named planes, but you need 3 points to name a plane. So these triangle planes, I just use all the points. So I'm going to say RUV counts as one. And the other one is, what is that? STW. You can put them in whatever order you want. So if you don't have to put them in the same order I do, but those 3 letters together respond to one plane. The other planes I see 3 more that I haven't talked about yet. I see the very bottom of the plane that is made up of UTWV. And then I see the one that's like vertical to it, like the back of the doorstop. RUST. So you just have to use any 2 letters to describe, or any 3 letters to describe those. So the bottom one I'm going to call UVW. And the side one I'm going to call RST, this back one right here, RST. I'm going to argue there's one more plane that we haven't looked at yet. And that's this like kind of slant one on top. The one that's made up of the points RSWV. So that's my very 5th plane. So we have a total of 5 faces, and 2 of them are the triangles in the front and back. One's the bottom and one's the back, and then one's the front, the top slanted side. So I'm going to call that RSW. I'm going to make you practice some of these later. So if you have any questions or concerns, please let me know. Next is vertices, which actually some of you might argue is easier than the faces. Each vertex is just each letter that you see. So I've got R, U, S, T, W, V. Those are all my vertices. Those are all the points. That's where all the edges connect. That's where all the faces have their corners. So we're going to call those the vertices. So R, U, S, T, W, V. And I count 1, 2, 3, 4, 5, 6 of them. And then last thing is edges, and those are just the sides of, or the, again, like the line, the segment where they connect. So I'm going to do all of the ones on one plane at a time. So I know that might be kind of confusing, but I'm going to do all the bottom ones first. So I've got UT, UV, TW, VW. So I'm going to list those 4 together. So I've got UT, TW, UV, VW. I've got all of those. Now I still see a handful more. So I'm going to do the rest that are on like the back, the like tall vertical face. So I've got RU, I've got RS, and I've got ST. And then it looks like I still have 2 more. I still have RV and I still have SW. So I've got to list those 2. RV, SW. All right, now I think I've literally touched every single line on here. So I'm just going to count how many I have. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 edges. I think if we were to spend more time here, we would have like a formula on like how to know how many faces, how many vertices, how many sides, blah, blah, blah. But I do not have that for you because we're not spending enough time here. So that's something you're interested in, we can look it up. But I think there's a pattern. We're just not talking about it today. Okay, anybody have any questions yet? All right, I need somebody to help me. Do you guys remember what the word regular means? Anyone remember that word? What does it mean to be regular?
Isn't that when like everything is congruent?
Mm-hmm. It means that all the sides are congruent and all the angles are congruent. So we've got 2 fancy words for that. We say equilateral
and equiangular or
and
equiangular.
equiangular. Very good. Equiangular. Awesome. And underneath them, just in case we forgot, I'm going to write what those are. So equilateral is all sides are congruent. And equiangular is all angles are congruent. Yeah, perfect. And we actually have 2 specific shapes that we like have names for those that are regular. So a regular triangle, we usually call an equilateral triangle. I don't know why we call it equilateral versus equiangular triangle, but like when you were back in like little like elementary school, you learned an equilateral triangle was where all the sides are the same. So equilateral is a regular triangle and it has 3 congruent sides and all of its angles measures are what? Does anyone remember what all my angle measures are if it's a triangle and it's equiangular? What would all my angles be?
60?
60, very good. 60 degrees. Once you have a 60-degree triangle, an equilateral, equiangular triangle, we can divide that into 30, 60, 90 triangles. So we had to learn special right triangles before we could get into 3D shapes because we're going to use the concept of special right triangles here. So let me draw a picture. Let me make this an equilateral triangle. Okay, we know all the sides are congruent and I know all the angles are 60. And what we're going to do is we're going to drop the altitude, drop a perpendicular down here. If that's true, then now instead of having 60, 60, 60, I now have a little triangle that's 90, 60, and then 30 because we split that in part. We split that apart. We will remind ourselves what 30, 60, 90 triangles look like momentarily, but we're going to have to use the concept of 30, 60, 90 to find like this side or this side or this side based on what's given to us. Okay, so you knew that. We just were reminding ourselves. And then a regular quadrilateral has 4 congruent sides and all of its angle measures are what? What's a 4-sided figure who has all congruent angles? What are those angles going to be? Quadrilateral that's regular. Anyone know the name of a regular quadrilateral? It has a special name that you guys have like known for a long time. what do we call it? Something that has all my sides are congruent and all my angles are congruent and it has 4 sides. Oh, we got shy again. That's okay. I'm here to help. All the angle measures are going to be 90 because remember in a quadrilateral, all the angle measures add up to 360. And if you divide it evenly by 4, we get 90. You're going to feel silly about this. It's a square. A square is what we call a 4-sided figure that has all my sides and all my angles congruent. Okay. Last one says every regular polygon with n sides can be divided into n congruent triangles. So we're going to do this. We're kind of going to mostly focus on a different shape that we don't even see here, but we're going to break it apart here. Okay, let's see. Each regular polygon can be, with n sides, can be divided into n congruent triangles. So right here, I've got a pentagon, 1, 2, 3, 4, 5 sides. So it's a pentagon with 5 sides. So I'm going to make 5 congruent triangles here. Congruent. What I'm going to do is I'm going to put a spot right in the middle. This is not exact, just pretend it looks more exact than it is. And I'm going to draw a line from the center to the vertex on all of these parts. So line, center to vertex, center to vertex, center to vertex, center to vertex. Okay. It looks okay. If I was better at drawing, it would look exact. I'm going to argue that this is 5 congruent triangles. So all of their bases all have a congruent side, the one that's marked with 1 blue congruent mark. All of their sides on the inside are congruent because it's the same distance from the center to the vertex in this regular polygon. All of these angles are the same. All of the outside angles here are the same, blah, blah, blah. And I have 1, 2, 3, 4, 5 of them. Okay. We're going to do it also in this next sided figure, which is 1, 2, 3, 4, 5, 6, 7, 8. This 8-sided figure, we're going to do the exact same thing. Remember, we call an 8-sided figure an octagon. So it's an octagon. And so I'm going to make 8 little congruent triangles. If you think you know what I did, I want you to try it on your own. I'm going to start by marking all the outside sides the same because they're all the same. Now, because of these shapes, in a minute, I'll tell you something different, but these 2 shapes, there's no reason to believe that the lengths on the inside are the same as the lengths on the outside. So I'm using different congruent marks to show that. I'm going to connect from one vertex to another. There we go. Good enough. I know it doesn't look exact, but pretend it's a little bit better. All of the sides on the inside are the same. And again, all of the angles in the middle are the same. And so now I have 1, 2, 3, 4, 5, 6, 7, 8. So I proved it. I'm showing you these 2 different examples because now the rest of the problems we're going to focus on are just triangles, just squares, and just hexagons. And the reason we did that is because with my special triangles, I can pretty easily find the area of one triangle. And so if I know that this octagon is made up of 8 equal ones, that I can find the area of that yellow triangle and multiply it by 8 to find the area of the whole shape. So that's why we're breaking up into smaller pieces, so I can multiply by how many triangles there are and easily find the area. Okay. Now, the one that we're going to do a lot of practice with is a hexagon. So the reason a hexagon is special is because it can be divided into 6 congruent equilateral triangles. And we know those little equilateral triangles are 60, 60, 60. Hint, we just did that like right up here. So I'm going to bring that kind of back to the front of our mind. If you want to think about it by splitting all of those 6 up into little 30, 60, 90 triangles, we would have 12 congruent 30, 60, 90 triangles. No, this only works for hexagons. Only works for hexagons. I'm gonna say that one more time. This only works for hexagons. So don't just try and do this on any sided shape because you can, only for a hexagon. Okay, so let's draw the example and then we're gonna do some examples from here. So I already drew to the center here. And so now I'm gonna finish drawing all the rest of my lines. Here we go, here we go. So again, you can see 1, 2, 3, 4, 5, 6. In this first one though, ooh, that was way too big of a eraser mark. In this first one though, you see that I could cut it down the middle to make a 30, 60, 90-degree triangle. That's what I have over here. So now instead of just drawing, I'm so sorry guys, my email is blowing up. So just like kind of let it be. I don't know if you guys hear it or if it's just me who's getting really annoyed by it, but it's like so frustrating. So I'm so sorry if you have to listen to it too. So instead of just drawing my 6 triangles, now if you drop an altitude in all of my triangles, there becomes 6 more little triangles for a total of 12 triangles. Again, I counted my 6 over here, but now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Everybody does a little differently. I tend to still use the 6 one. And I realized that last period when I just kept doing 6, but you can do 12 just as easily. You just have to be very cautious of something. And once we do a problem, I'll show you what that means. Okay. Before we get in here, I'm going to remind you our 2 special right triangles. So I've got 45, 45, 90. And I've got 30, 60, 90. And if you don't have this memorized, I'd write it down. Now, we did not make you memorize this earlier, so I don't think we're going to make you memorize it now. I think there's other things we might have you memorize. So I plan to put this on stuff, but just like we've been doing this long enough, you should kind of have an idea of what's going on too. In a 45, 45, 90, my legs are the same. And my hypotenuse is x root 2. So in order to go from the leg to the hypotenuse, we're going to multiply by root 2. And then in order to go backwards from the hypotenuse to a leg, it's the same for either direction. I just think it's a little cleaner to do it this way. We're going to divide by root 2. Similarly with the 30, 60, 90, the side that like we're always basing things off of is across from the 30-degree angle. My long leg across from the 60 is x root 3, and my hypotenuse is 2x. So in order to go from the short leg to anything, you're multiplying. So short leg to hypotenuse, multiply by 2, short leg to long leg, multiply by root 3. If I'm going the other way to get to the short leg, you're always dividing. So long leg to short leg, divide by root 3, hypotenuse to short leg, divide by 2. Notice there's no connection between these two. All right, that was your SparkNotes version of special right triangles. Anybody have any questions yet? All right, I want to get through all of these examples, so we're going to keep moving. Okay, first thing, and I'm going to look at the first 2. I think perimeter is super easy here. So if I already give you one of the sides, these are regular polygons, which means all of their sides and all of their angles are the same. So that means that all of these have sides that are 8. So 8, 8. And this one is 10, 10, 10, 10, 10. Now you can just add 8 plus 8 plus 8, or I know that it's one side is 8 and there are 3 total sides. So I'm going to think of perimeter as 3 times 8. 3 times 8 is 24. I don't have any units here, but I'm going to put a little U to represent that I need to remember my units. Some of us missed that on the last quiz, which I will pass that back on Wednesday. Whenever I see you next, I'll have your tests. I'm going to do the other one at the same time because it's super easy. This time my perimeter is 10 and there's 1, 2, 3, 4, 5, 6 of them. So I'm going to do 6 times 10, which is 60 units. The next one looks a little tough, so I'm not going to go do perimeter for that. I'm going to come back and do my area for these two before I move on. Anybody questions on perimeter? Okay. Now I'm going to take my triangle. It's an equilateral. I'm going to drop my altitude. The only way we know how to solve these with the triangles is if it's a 30, 60, 90. So I'm going to give you 30, 60, 90. There's 60, there's 30. I knew this entire bottom was 8. So that means half of it is this leg right here. So that's 4. Remember that when you go from the short leg to the long leg, you have to multiply by root 3. So 4 times root 3 is just 4 root 3. Now, area of a triangle is the same thing. 1/2 base times height. 1/2 base times height. Now, you can use this as one triangle, but then that means that my whole shape now has 2 triangles. So I'm gonna have to end up multiplying it by 2. I would rather think, and this is what I was saying a minute ago, that I tend to do the whole 60-degree, 60, 60, 60 triangle. So I'm gonna say my base is 8 and my height is 4 root 3, and that takes into account the entire triangle. So I'm gonna do 1/2 of 8 times 4 root 3. 1/2 of 8 is 4. 4 times 4 is 16 root 3. So my area for this shape is 16 root 3 units squared. Any questions yet? Okay, we're going to keep moving. Let's look at the next one. I've got a hexagon here, which means that I'm going to have another 60, 60, 60 triangle. Once I told you that, you should just assume every hexagon is going to use the fact that I've got this 60-degree by 60 by 60 degree triangle in here. You can draw a triangle separately if you want, but I think I've got plenty of room to draw in here. So I'm going to draw my altitude. Got my 90-degree angle. I've got my 60, I've got my 30. This entire length is 10, which makes my short leg what? Does anyone know what my short leg is going to be? Thanks, Kate. It's going to be 5. Then I take my short leg times root 3 to get my long leg. So I get 5 root 3. And so my area here is going to be 1/2 times, and again, I like to use the whole triangle. I'm going to do 1/2 of 10 times 5 root 3. Now that's just the area of the little triangle, the highlighted yellow triangle. I have a total of 6 triangles though. So whatever the answer to this is, I'm going to multiply it by 6 to represent my 1, 2, 3, 4, 5, 6 triangles. 1/2 of 10 is 5, so I get 25 root 3 is the area of one triangle. I have 6 of them though, so I need to do 25 times 6, which is 150. 150 root 3 is my area. 150 root 3 units squared. Okay, anybody questions yet? All right, let's keep rolling. I got another one. This time I didn't tell you the side of the triangle. I told you part of the distance from one vertex to another. I'm going to challenge us to do this. Let's finish this line. When I finish this line, I also have 10 over here, but now I have a little right triangle in here. I can use the fact that I've got a right triangle in my square. And if you remember, squares make 45, 45, 90-degree triangles. So hexagons make 30, 60, 90. Equilateral triangles are 30, 60, 90, but a square is 45, 45, 90. Remember, 45, 45, 90, the hypotenuse is x root 2. And so to go from the hypotenuse to one of the legs, we're going to have to divide by root 2. My whole hypotenuse is not just 10, it's 10 plus 10, which is 20. So I'm going to do 20 divided by root 2 to get the length of one of my legs. Here's a leg, here's a leg. So multiply by root 2, multiply by root 2, I get 20 root 2 over 2. 20 and 2 cancel out to be 10, so I get 10 root 2. as my sides. 10 root 2, 10 root 2. Cool. That makes my perimeter super easy because I know that all my sides are the same length. So my perimeter is going to be 4 times 10 root 2. That becomes 40 root 2 units. Now you can use the area of a triangle here, but again, kind of like that first problem where I was like, let's not make it harder than it has to be. I'm just going to do the area of a square. The area of a square is side squared or side times side. It's the same thing as a parallelogram. It's the same thing as a rectangle, base times height. So I'm going to do 10 root 2 times 10 root 2 to get my area. Remember, you multiply the numbers outside the radical first. So I get 10 times 10 is 100. Then you multiply the numbers under the radical together. Root 2 times root 2 is just 2. So 100 times 2 is 200 units squared. I'm trying to do all types of examples that you're going to see on your homework. Does anybody have any questions yet? All right. Since we just did a square, we're going to skip to this square right here, and then we'll do the 2 hexagons. Now, I'm going to argue this one is even easier than the last one because I didn't give you a slant distance. I gave you a straight up and down distance. So now we can finish this distance by continuing this line that's also 2 root 6. Do you notice how this line is the same distance as this line, which is the same distance as this line? And if I could turn it, it'd be the same distance. I guess no, I can't turn it. Maybe I can. Now it got bigger, but pretend like it's the exact same distance as this and this. It's a square. All the sides are the same. So even though it's in the middle of the shape, 2 root 6 plus 2 root 6 is the same distance as this length out here. We just practiced multiplying 2 radicals together. So reminder, when you add 2 radicals together, you get to add the numbers out front and then the numbers under the radical stay the same. So I've got 4 root 6 is the answer. And that's what all of these sides are: 4 root 6, 4 root 6, 4 root 6. Once we found the outside, just like the last problem, you can easily find perimeter and area. So take 1 second and try that on your own. Take 1 second, you try that on your own. Okay. If anyone wasn't sure where to start, let me start with you. Remember, perimeter, you just add up all the sides or take one side and multiply it by how many there are. So I'm going to do 4 times 4 root 6, which is the same thing as 16 root 6 units. And then area is 4 root 6 times 4 root 6. Again, you can make it 2 triangles if that makes you happy. I just don't want to do extra work if I don't have to. So I've got 4 times 4 is 16, and then root 6 times root 6 is 6, and 16 times 6 is 96. So I've got 96 units squared for my area. All right, I've got 2 more perimeters. So I want to do, or sorry, 2 more hexagons. So I want to get into those. Before I keep moving, does anyone have any questions? Okay. Remember, squares can be 30 or 45, 45, 90. Hexagons are always 30, 60, 90. So let's do the one on the bottom left first. So right here, I've got my side, my little distance from the center to the vertex or vertice is 14. I'm going to make my triangle up here. I did it below last class and it got a little confusing because 14 is kind of far away from its line. It's a hexagon. So remember, it's equilateral. This, and this are all equal. So this is also 14. This is also 14. Now the problem is I'm about to make a altitude, which means that I've got a 90 degree here. This is 60 since I haven't touched that angle, and this is 30. I got to find my short leg first, which is easy in these hexagons. Does anyone know what the short length is? The whole side's 14. What's the little bitty side? Getting afternoon tired? 14 divided by 2 is 7. And then to go from the short leg to the long leg, I have to multiply by √3. So this becomes 7 √3. Again, this is where I like to do my area using my height and then the base of the entire bottom side. So I'm going to multiply it by 6. So I've got area of the triangle is 1/2 base, which is 14 times 7 √3. And then whatever that answer is, I'm multiplying by 6. 14 divided by 2 is 7. 7 times 7 is 49 √3. And 6 times 49 is going to be 294 √3. I didn't do perimeter yet, which I should have done earlier. It was pretty easy to do earlier. The minute I realized that this was 14, then I knew all of the sides were 14. So for perimeter, I'm just going to do 6 times 14, which is going to be 84. 84 units. All right, I've got time for just one more problem. Any questions yet? Okay. This last problem is another hexagon. You can count all the sides up. This time though, I gave you the short angle or the short leg. No, I lied. I gave you the long leg, not the hypotenuse, which is normally what I give you. So I gave you that the short leg is 6 √3. I know, oh my God, I said that wrong again. The long leg is 6 √3. It's across from the 60. What we need to do is find the short leg. We've gone the other way around. We keep, where was it a minute ago? We multiplied by √3 to go from 7 to 7 √3. Up here, we multiplied by 4 to get 4 √3. Over here, we multiplied by 5 to get 5 √3. Now we're going to go backwards, and the opposite of multiply is divide. So instead of multiplying, I'm going to divide my 6 √3 by √3. Divide by √3. 6 √3 divided by √3, my √3's just cancel, and I'm left with 6. Now 6 is not the entire length. So you can either find the area of this little triangle and multiply it by 12, totally great option. Or you can do what I've been doing this whole time, which is taking the whole 60-60 triangle and multiplying it just by 6. My little thing is 6, which makes my entire long side and all of these little pieces 12, 12, 12, 12, 12, on and on and on. The reason that's helpful is now when I do area, I'm going to do area of 1/2, 12, which is my base, times my height, which is 6 √3. And again, I'm multiplying that by 6. If you only did this little triangle, then you'd multiply, ooh, that's way too big of an eraser. Let me make that smaller. You'd put the 6 in here, and you'd put the 12 out here because there's 12 little guys. It all works its way out in the end. Just be super careful about what you're doing and have intention with it. 1/2 of 12 is 6, so 6 times 6 is 36 √3, and 6 times 36 is 216 √3. So my area here is 216 radical 3 units squared. And then perimeter, again, it was really easy a minute ago. As soon as I realized all my sides were 12, I'm going to do perimeter is 6 times 12, which is 72 units. Okay. I know I did that quickly, but I wanted to review our inscribed quadrilaterals earlier. And then a reminder, we just did all of these examples. I did 6 examples with you. Your homework looks a lot like that, there's a lot of space. If you don't have work, you're probably doing something wrong. So make sure you have just about as much work as I had on mine. And I've got an example that looks just like all of the ones I did in class today. On the back side, there's just some vocab, just like the very first couple problems we looked at in our notes. Okay. That's it for today. Does anybody have any questions? Okay, well, I will see you tomorrow. No, I lied. Wednesday in person. If you need anything, I'll be around for a minute. If not, have a great day. Bye, guys.